This machine was built to survive the impossible. It cost $135 million, took years of flawless precision engineering, and was designed to withstand the violent vibrations of a rocket launch and the brutal, freezing vacuum of space. But this satellite never made it to orbit. It did not explode on a launch pad. It was not struck by a rogue asteroid. It was badly damaged while sitting quietly on a pristine factory floor. It simply fell over. And the reason it fell reveals a terrifying truth about how the modern world is held together. To understand how a multi-million-dollar spacecraft can just tip over like a poorly balanced bicycle, you first have to understand the sheer scale of precision involved in building one. This was NOAA N-Prime, a cutting-edge environmental satellite designed to orbit Earth, tracking severe weather patterns, monitoring climate change, and providing critical data for search and rescue operations worldwide. In the aerospace industry, the environment where these machines are born is treated like a temple. These are called clean rooms. The air is filtered constantly because a single speck of dust landing on a sensor can ruin a years-long mission. Every tool is catalogued. Every movement is calculated. Billions of mathematical calculations dictate how these metals are shaped and joined. When you look at a satellite, you are looking at the absolute peak of human capability. There is no room for error, no margin for guesswork, or so we like to think. It is September 6, 2003. Inside a high-tech manufacturing facility in sunny California, NOAA N-Prime is undergoing routine preparation. Because satellites are awkward, heavy, and incredibly fragile, engineers don't just lift them by hand. They secure them to a massive, specialized piece of machinery known as a turnover cart. Think of it as a heavy-duty, highly engineered mechanical cradle. The task for the day was simple. Rotate the satellite from a vertical position to a horizontal one so technicians could work on its instruments. It was an operation that had been performed dozens of times before on this exact cart, with this exact type of spacecraft. The team entering the clean room that morning wasn't a group of amateurs. They were highly trained, veteran aerospace technicians. They logged into the system, checked the status board, and reviewed the paperwork. Everything looked perfectly normal. The paperwork indicated that the satellite was ready for rotation. The cart was in position. The atmosphere was calm. There were no warning signs, no alarms. The engineers relied on the system. They believed the environment around them was secure, protected by layers of bureaucratic protocol and rigorous corporate design. They had no reason to suspect that beneath this illusion of absolute order, a catastrophic oversight was already waiting for them. The operator pushes the control button. The heavy electric motor hums to life. Slowly, the 1,500-kilogram satellite begins to tilt. 10 degrees, 20 degrees, 30 degrees. For the first few seconds, physics behaves exactly as expected. But as the angle increases, something fundamental changes. The center of gravity shifts. Suddenly, there is a sound that no aerospace engineer ever wants to hear. A loud, sharp, metallic crack. The satellite isn't rotating with the cart anymore. It is sliding off it. In a fraction of a second, years of human labor and $135 million of taxpayer money accelerated toward the floor. An object engineered to survive the violent, explosive forces of a rocket launch into the cosmos was utterly defeated by a 3-foot drop on Earth. The satellite slammed violently onto the hard concrete floor of the clean room. Panels crushed, delicate instruments shattered, gold foil tore open. The silence that followed in that clean room must have been suffocating. When NASA launched an official mishap investigation, they expected to find a complex structural failure. Perhaps a metallurgical defect in the cart, a software bug in the rotation sequence, or a sudden hydraulic failure. Instead, they found something far more primitive. 24. That is the number of missing bolts that destroyed NOAA N-Prime. 24 simple mechanical fasteners that were supposed to lock the satellite's adapter plate to the handling cart were completely absent. The satellite wasn't bolted down at all. It was literally just resting on top of the cart, held in place by nothing but friction and gravity, until the tilt angle made that impossible. But how does a room full of rocket scientists forget to bolt down a satellite? The truth is much more disturbing than a simple case of forgetfulness. Days earlier, a completely different engineering team had needed to use the turnover cart for a separate operation. To do their job, they had to remove the 24 bolts. When they finished their shift, they didn't put the bolts back. Crucially, they didn't document the removal in the cart's central logbook, and they didn't update the physical status board on the cart itself. When the next team arrived days later to rotate the satellite, they looked at the paperwork. The paperwork said the cart was ready. Because the system told them it was safe, they assumed it was safe. No one looked down at the actual metal to check if the bolts were physically there, and here is the part that makes the accident even harder to believe. According to the investigation, one supervisor actually noticed that some bolt holes were empty. He mentioned it, but the concern was dismissed and the procedure continued. The warning existed. The system simply failed to listen. Everyone assumed that someone else had already checked. It is easy to blame the technicians who pushed the button that morning. It's easy to call them careless. But the official investigation concluded that this was not a failure of a single individual. It was a design failure of the system itself. In modern engineering, as systems grow more complex, we create layers of bureaucracy, checklists, and procedures to keep us safe. But these very layers create a psychological trap, known as the illusion of redundancy. When responsibility is distributed across too many people, too many shifts, and too many pieces of paper, individual accountability begins to dissolve. If 5 different people are supposed to verify a safety check, each person starts to perform a shallower inspection, subconsciously believing that the other 4 must have done it right. When responsibility belongs to everyone, it ultimately belongs to no one. This story forces us to look at the invisible world around us with a slight sense of unease. How many invisible bolts are holding together the world we trust every day? The airplanes we sleep on, the bridges we cross during our morning commute, the power grids that keep our cities alive, they are all held together by the assumption that the person before us did their job perfectly. Modern disasters rarely begin with an explosion. They begin with a silent gap in a checklist. The NOAA N-Prime satellite was eventually rebuilt, costing taxpayers an additional $135 million to fix the damage. It eventually launched into space under a new name, finally fulfilling its mission to look down on our planet. But the ghost of its fall still haunts the engineering world. It stands as a permanent reminder that the most dangerous vulnerability in any advanced design isn't found in the software, the hardware, or the materials. The satellite did not fall because engineers lacked intelligence. It fell because complex systems have one fundamental weakness that no material can ever eliminate: human assumption.